So we are now ready to start looking at area approximation using sigma notation. So let's recall that to estimate the area under a curve y equals f of x on a closed interval from a to b, such that f is continuous everywhere on this closed interval, and f of x is greater than or equal to 0 for all x values within this interval, then we've seen that we can approximate the area under this curve by using the width of the subinterval multiplied by the sum of the heights. And again, if we were to expand this out, all that we're doing is we're taking the sum of all the areas of each individual rectangle. Right, so we can think about this as, in shorthand, this is the width, delta x, multiplied by the sum of the heights. So I have f of x sub 1 plus f of x sub 2 plus, and we continue all the way till we get to that last height, we'll say f of x sub n. So now that we've been introduced to sigma notation, we can take this one step further and rewrite this in a summation notation. So we can say that this is the sum from, so now we want to establish the index of summation. So notice we're starting at 1 and going to n. So we can say that this is the sum from k is 1 to n of the width. Now notice here again, we've used the heights to come up with the index of summation. So we can say, we'll use this for our general formula. We can say the width is a constant, but the thing that's changing is our height. So that's f of x sub k. So, again, this is for a finite number of rectangles. But we can get a more accurate area. We can, in fact, get the exact area if we let the number of rectangles approach infinity. So let's think about this real quick. We can make a little love note here to ourselves that as the number of subintervals increases, so the number of rectangles or the number of subintervals increases, and so we can shorthand and say that as n varies towards infinity or approaches infinity, the width of each subinterval decreases. The width of each subinterval decreases, or more specifically, approaches 0. Say that delta x approaches 0. So as the number of subintervals increases, the width of each subinterval approaches 0. So this is going to give us an exact area. So if we take, or we can say that the area is exactly equal to the limit of this finite sum as n approaches infinity. So you have the limit as n approaches infinity of the sum from k is 1 to n of the height f of x sub k multiplied by delta x. And so this is the idea behind Riemann's limiting process to get that exact area. And so we call this here, this is Riemann's formula. And this is Riemann's limiting process. So it's important to note before we go ahead and look at examples that we're going to need to consider what's going on in that kth subinterval. All right, so here we go. Let's suppose again that we want to estimate the area under the curve y equals f of x on a closed interval where x is greater than or equal to a, less than or equal to b, such that f is continuous everywhere on this interval. So, just as we did before, the first thing that we want to do is divide this interval into n subintervals. And we're pros at this now. So we know that this is going to start at x naught and it goes to x sub 1. Our second interval is going to be x sub 1 to x sub 2. And we continue in this manner. And somewhere in here, we're considering that kth subinterval. So it's going to be the interval x sub k minus 1 to x sub k. And all the way to our last interval, which is going to be x sub n minus 1, x sub n. And so it's particularly important to note our kth subinterval here. This is what we're going to use with Riemann's limiting process to find the height and confirm our width. So in step 2, we use the kth subinterval to define the height and the width. So our width is going to be the difference of the endpoints in the kth subinterval. So we can think about this as delta x sub k, and that's going to be the length of your interval, so x sub k minus x sub k minus 1. And then the height is going to be the function evaluated at the kth point in the kth subinterval. So our height is going to be y is equal to f of x sub k, and this is such that x sub k is in that kth subinterval. So looking at how we've defined this above, it's going to be our right-hand endpoint. But you could also use a left-hand endpoint. It all depends on how it's defined. So then last but not least, we want to use those algebraic properties of finite sums to find a formula for the Riemann sum. And so that's going to be defined by the area approximation. So we know that the area is approximately equal to the sum from k is 1 to n of the height of that kth subinterval, f of x sub k, multiplied by the width of that kth subinterval, delta x sub k. So this is our Riemann's sum. So that's our Riemann sum. And again, to get the exact area, we then apply the limiting process to this summation. So let's go ahead and take a look at some examples.